Well, this app is also about ANOVA. It's very, very similar to what you have seen before. You can see even that the initial values are the same here for this case. However, the difference is, first of all, I do these calculations without this unbiasing part. So I use with the original numbers. And I also showed you a couple of extra things. For example, this cuckoo plot for residuals, which we normally use for quality check of ANOVA model. Okay. So very quickly then. So this is the systematic part. And in this case, I don't have this +5, 0, and -5. I have the real values, right? So but the idea is the same. The number of degrees of freedom is 2. Why? Because the average of all these values is 100. So it means that this value depends on these two. If I know these two values, 100 and 105, I can simply take, so in this case, I can take just 300 minus 100 minus 105, and I will get 95. Every third value in this matrix depends on the other two. So therefore, I have only 2 degrees of freedom. I have only 2 independent values here. And then the sum of squared values is the same, because how to compute sum of squared values in this case? Since this is unbiased data, I need to subtract 100 from every value, right? You remember variance, it's when you take a value, subtract mean, because you measure distance, how far this value is from the mean, and then you square this distance, and then you divide a sum of squared distances to the degrees of freedom, right? So the 495 minus 100, and this is the average of these values, will be -5, and then it will be -5 in all these cases. So from that point of view, this value is identical to what I got here. I got in the previous video, in the previous app, and then this is the mean squared. This is the variance. Again, it's the same. Then similarly here, right? So the residuals are absolutely identical to what we had before, because how we got this -10? It's the original value 85 minus the average for this group 95, and that gives you -10. This is what is rest after you remove the systematic variation from the original values. And then you can see all the calculations are the same. And now I moved the test plot here, so you can see the same f value, you can see the distribution of f values, and then you can see the p-value and so on. What is also new here, it's this plot, and this is a QQ plot for these values, for these residuals. QQ plot, it's a quantile normal probability plot. What you see here, it's a normal quantiles, it's simply z-scores. So you can see that, for example, this z-score is -1, this is average, this is +1, 2, and so on. And these are the real residual values. And the point is that if these values came from normally distributed populations, they should lie very close to this ideal line that you can see as a dashed line, right? And that's the way to check the normality, for visual checking of normality. You remember that this data, initial data, I made it artificially nicely looking, so therefore this, you can see clearly groups in this case, right? But if you take a new sample, which will be random, you can see that the groups are not, we still have some strange behavior. So this is why we always need to supplement the cuckoo plot with normality test. But you can see that these points lie very close to this straight line, right? So in this case, there is no such big deviation from normality. And then sometimes you can see they look nicer, like in this case. Sometimes maybe this is also quite nice, and sometimes you can see some outliers. So that's the point, right? So when you take a random sample, if sample size is not very large, you will always see some strange behavior like for these points, okay? But this is absolutely normal, because this is just how the random world is. And therefore, just look at this plot, but also supplement it with normality test. So this is very important plot for quality check of your ANOVA model.